Good afternoon, friends and neighbors. Well, maybe good morning, depending on where you are. Time now for another networking video. Today we're going to be doing tool time, and the tool we've chosen for today is ping. Now, as you can see, the cat here is really excited because ping is sort of a lackluster tool until you maybe take a little deeper look at it and understand some of the other capabilities that are embodied in this rather inobtrusive tool. So first up, what is ping? Well, ping is a program that generates ICMP echo request packets. The target machine has this built-in responder function. So anything that has an IP address that has ping programmed into it, the whole idea is that I send you an ICMP echo request packet and then you respond with an ICMP echo reply. That's it. That's all that ping does by default. Now, sometimes we can get tricked into thinking that ping does more than that because sometimes other traffic happens when we do our pings or when we generate ICMP echo requests. But the extra traffic that's generated actually has nothing to do with ping. It has everything to do with the node that you're sitting on wanting to communicate with another node. And the thing that I'm talking about most is ARP. So sometimes we generate ARP traffic, sometimes we don't. We'll do a test later on and see exactly what we mean by that. In addition, to follow up, maybe on that idea, is that lots of things cause ARP traffic to be generated. Anytime you want to talk to anybody, you generate ARP traffic. So ping, ICMP echo request, and ICMP echo reply, and that's it. So we have a bunch of ping options. Now, by default, what we usually do is ping and then an IP address, and that's all we think about. But as you can see here from the help page, ping has a lot of options associated with it, and we're going to do a test with several of these. Now, some of these are really quite useful. They're very handy to help tailor the test that you're doing. Some of them are just kind of cool, and we'll do a little bit of both. So the default behavior of ping depends on the operating system. But essentially what's going to happen is that whatever operating system you're on, you're going to generate an ICMP echo request. And then, of course, you're going to get the ICMP echo reply. Now, if you're sitting on Windows, you're going to generate 4 ICMP echo requests. Not all in a row. You'll do an ICMP echo request, and then you'll get a reply. So that's 2 packets. But you're going to do that 4 times. So 4 plus 4, that gives us 8 packets. Another interesting thing about the Windows default ping is that it's 32 bytes of data. And the bytes of data are actually parts of the alphabet. So when you're looking at traffic and when you're trying to understand who is talking or maybe even who is pinging, you can tell a lot by just looking at the style of the ICMP echo request. Linux, by default, typically does a continuous ping, meaning that it doesn't stop until you stop it. And a lot of times it also tries to do name resolution. And the ICMP echo request data is actually larger, typically 64 bytes. And sometimes we can also look at the payload. Sometimes the payload is a little bit different. Now, a really handy thing to remember is that almost anything that has an IP address can be pinged, and you can ping from. Now, that's not always the case with small devices that just have an IP address sort of coded into their networking stack. But if you're working with a production router, like a Cisco router or a Juniper or something like that, then you absolutely can ping from that router. Now, we often think about switches as being layer 2 devices, and they are, unless we're talking about a multi-layer switch. But even if you've got a layer 2 device, like an access point or a switch, and you give that thing an IP address, you can ping it. And in most cases, you can ping from it as well. So great debugging tool to test to and from your network devices too. So don't forget that. Now, one of the reasons that I talk about the default behavior for different operating systems and different devices is because when bad guys are trying to figure out what's on your network, a lot of times they'll do something called fingerprinting. And that is simply trying to understand by communicating with the device what its behavior is. And by looking at the differences in the behavior, you can identify the kind of device. So if I ping an IP address and get a particular response, I know that it's a Windows box or a Linux box, or a Cisco router, for example. So these are important things to realize when you are trying to understand, network traffic and how things are maybe identified. This is one of the reasons why some network administrators turn off the ability of a device to respond to ICMP traffic. So what is an ICMP echo request and reply? Well, here they are. Right? These are just inside a standard IP packet, and you can see on the left that we've got an ICMP echo request. So it's a type 8 code 0 ICMP message, and there is our alphabet content. So it's just hexadecimal values for letters in the ASCII table. And there's our 32 byte size, so we know this came from a Windows machine. Here is the response to this echo request. So it's an ICMP echo request, type 0, code 0, same response. So this is what we expect to see when we're using ping in terms of ICMP echo traffic, and of course this is the default. We'll see here in a second that we can manipulate this quite a bit. Okay, so let's run some tests, some experiments, and see what the output is on the command line, and then we'll also do the network traffic at the same time. So the first thing that we'll do is the ARP table versus ping. So here we go. Alright, so what we can see here is that I've got Wireshark running and I'm filtering on ICMP or ARP traffic. And I've got my ARP table here. Now, when I've got my ARP table, in my ARP table, I can see that I've got 15.1 here. So what I'm going to do is delete 15.1. And if I take a look at my ARP table again, we can see that 15.1 is missing. So now let's ping that address and find out what happens. We can see in Wireshark that I generated this ARP traffic. And I'm looking for 15.1, and 15.1 responded, and then here are my 8 Windows packets. Well, if we take a look at my ARP table again, we can now see that 15.1 is in there. But what happens with traffic? Remember that we got packet 310 over here. What happens if we ping the same address? And we can see that this time we just generated the ICMP echo request traffic. So we've got a fun little idiosyncrasy of Windows 10 here, but the important thing that we want to look at is that initially we had no entry in the ARP table, right? And so we had to ARP. And the whole reason that we ARPed was to find a MAC address so that we could build the frames. And then we saw the ICMP traffic. Now here at packet 406, we can see the second ICMP echo request going out, but there was no ARP traffic that was a precursor to this. Now Windows 10 went ahead and ARPed again just to make sure we had the right MAC address, but the important thing is that it didn't have to do it first. Now Windows 10 and a lot of modern operating systems modify their behavior when they're populating ARP tables and when they're populating routing tables, but this is what I wanted you to see. Okay, so that's one detail about ARP traffic. So when we see this, we might have said, oh, well, ping generates ARP requests. That's not true. Ping generates ARP requests when it needs to, but the same thing is true if you go to a web page or you go looking for DNS answers or anything else. So there we have it. And the proof is in, this packet number right here. It's well after what we did first. Okay, so let's try our next test. So the next two that we're going to do are the ping-l. We're going to change the size of the packet, and then we're also going to change the count. So this count is very, very handy. And while we're at it, we'll also do a continuous ping. Now, most operating systems have these same options, but a lot of times they use different letters. So here we go. So the first one up is we'll do a ping-n, and we'll just do 2 to the same address. And you can see what happens here is that we're just generating 2 of the ICMP echo request and reply pairs. That's it. That's all we're going to do. Now the reason that this is handy is mostly because I don't want to wait for all of this other traffic to happen. If I believe that the node is alive, I might even do a ping minus n1, and then it only sends one at a time. All right, let's do, we'll add ping-t while we're at it. And ping-t is a continuous ping, so this will just go until I stop it. So we can see we're well beyond my original 4. Okay, so we're going to go ahead and stop that with a Control-C. The next thing that I'll do is we'll do a ping-L. Now a -L is the size. Now the fun thing about the size here is that I can get out beyond the Ethernet minimum frame size. And that causes me to generate a couple of frames for each ICMP echo request that goes out, because the maximum size of an Ethernet data field is 1500 bytes. So here we go. Now, it looks like it's the same. I'm going to stop this capture. This is what we want to see here, but I need to get away from just ICMP here for a sec. So I'm going to clear this, and we're going to go to, well, let's actually get our packet number. Okay, so let's look at our packet numbers real quick before we go diving back over there. We can see that packet number 213, this exchange here was a standard or default ping, and we can see that it's quite small. But the minute I go to 302, this is the outbound, look at the size of the data. So we know that this is actually what we're after. So we're going to go down to packet 302 and see what we're after. All right, so here is packet 302. But look at what happened immediately before that. And so this shows us what's actually happening. Now when we adjust the size of the ping, one of the reasons that we do that is to experiment with fragmentation. And so what we're looking at here is two packets that actually go together. Now when I generate a ping of 2000 bytes and the maximum Ethernet frame is 1500, I know that I've got to generate 2 Ethernet frames to do that. So that's what we're seeing here. Well, how do I know that? Well, I did a fragmentation video on this, but you can see it right here that I've got the flags that indicate that there's more fragments. And if I take a look at the identification, 3608, 3608. So these two go together. And here is the response, 204D, also more fragments, and then 204D right here. Now, it's not both of them that have the ICMP header, which is why this fragment did not appear when I was filtering on ICMP. So there you have it. So that's a very interesting thing about the ping-L command. So some of the other options that are actually kind of cool are ping-R, ping-J, and ping-6. Now this also works. This is an IP version 6. You don't actually need the -6. The minute you ping an IP version 6 address, it goes ahead and does it. But ping-R and ping-J are interesting for a completely different reason. We are used to seeing an IP header of 20 bytes. These two change that because they're adding options in the IP header, and it's one of the few times that you'll see the IP header expand. Now I'm going to clear my screen here and start a new capture, and we're going to do ICMP again. We're going to do a ping-R and a ping-J. Now it won't work because the network's not set up to support these options, but I'm going to show you what happens when you do that. So if I do a ping-R, for example, and then I say we'll record a couple of hops. So we want to do maybe, I don't know, 3 hops. Now ping-R is the record route. Maybe what I'll do is this. Okay, so ping-R is this one right here. So what I'm going to do is ping-R, and then we'll say, well, we want to do 2 or 3 hops on our way to 8.8.8.8. What this is going to do is expand the IP header to say, tell me about the hop. It's very similar to what you would get from traceroute, but everybody along the way has got to support the options, and most routers today don't, but it's kind of fun, and if you do actually have routers that'll do that, or you want to set it up in the lab, you can. So here we go. So we can see that this is going. I've got traffic that's being generated here, but nobody's really answering out. And the reason for that here will become obvious in a second. So we'll let this finish. There we go. So let's take a look at some of the traffic here. Now at this point I don't actually care about the ICMP. It's the standard ICMP echo request, but here is the interesting part. Normally the IP header is 20 bytes in size and it would end with a source and destination IP address. But look right here. We've asked the paths along the way to tell me about themselves a little bit. So these are the record route options that would actually fill up. So this is one of the few times that you would see the IP header go beyond 20 bytes. And these are some of the options. But of course the router's got to support it. Okay. Well, let's do something else here. I am going to we'll do a quick partial trace route. Now I don't really care about the output of trace route except for the first couple of hops. So we can see the trace route is going here. You can take a look at the other videos on trace route to see how this is working. And this actually is what we expect to see in a trace route. So this is not failure, this is trace route doing exactly what it's supposed to do. There we go. So what becomes interesting is that I've got these IP addresses along the way. So now if I do ping-j, now ping-j says I want to do source routing. Well, actually we'll show that to you. So down here we can see ping-j, and what -j says is I don't want to depend upon sort of default routing to handle my traffic. I want to go along a particular pathway. And the pathway that we might take is this right here. So if I say ping-j, and then maybe, what is that? Well, I'll do my default gateway, and then I'll say like this. Now, if there was another pathway, I would be specifying where I was going, or the pathway that I would actually take. So let's say that there were forks out there. Then I could specify the path for this traffic. And it's a good way to test a particular pathway. But, again, the routers have to support it. And then where am I going? To here. And we'll see, we're at packet 645 here. We'll see what actually happens. Fire away. We can see traffic's being generated, right? It's right there. There's our first one that's being generated. We go ahead and click on that, and we can see it's the same thing. Here is the source route information, and this says, I want you to go this way. Now, the traffic along the way has to support these options in the IP header. It's not just a matter of supporting, our standard ICMP echo request anymore. It is a matter of saying to the router, I'm going to specify which way I want to go, and you have to support my desire to have you read these particular headers in the IP packet. Most routers don't unless you turn this feature on. And so there we have it. So again, it fails, right? Just like the previous one failed. Oh, I think I cleared that. But there we have it. This is another one of those instances where you'll see the IP header actually expand. So that'll do it for the experiments for today. We got some really useful stuff, right? Ping-L, ping-C, ping-T, and then some that are just kind of cool. Ping-R, ping-J, if you want to set that up and see how actually the IP header options work. And of course, if you are in IP version 6, don't forget that you've got ping commands there too. Hey, how about that ping, huh? Nice way to send about our echo requests and echo replies. It is our go-to test tool. We use it all the time, but now maybe we realize that there's a little more to it, and maybe we also understand what ping is actually doing. You can make use of lots and lots of options to tailor that test to be exactly what you want it to be. Hey, thanks for watching. Thanks for listening. Like and subscribe if I helped, and may those packets always reach their destinations, especially if you're trying to ping somebody. By the way, I'm adding a new channel just for fun. It's music that I like to listen to when I'm working or fooling around in the lab. So let me know what you think.